2. Ya, 3.
Selamat datang di Fakultas Pertanian Universitas Pembangunan Nasional Veteran Yogyakarta. Fakultas Pertanian adalah salah satu fakultas tertua di UPN Veteran Yogyakarta. Berdasarkan Surat Keputusan Menteri Urusan Veteran RI Nomor 139/KPTS/tahun 1998 tanggal 15 Desember 1958 diresmikan UPN Veteran Yogyakarta sekaligus tonggak berdirinya Fakultas Pertanian. Perubahan status UPN Veteran Yogyakarta dari perguruan tinggi swasta (PTS) menjadi perguruan tinggi negeri (PTN) membawa konsekuensi strategis yang besar. Penegrian merupakan tantangan yang menuntut peningkatan kinerja dan partisipasi yang semakin besar lagi dari seluruh sivitas akademika dan pegawai UPN Veteran Yogyakarta pada pembangunan bangsa. UPN Veteran Yogyakarta terus berbenah diri untuk menjadi PTN yang tetap melestarikan kredo kampus, disiplin, kejuangan, dan kreativitas. Sebagai salah satu fakultas yang lahir dan besar bersama tumbuhnya UPN Veteran Yogyakarta, Fakultas Pertanian memiliki visi menjadi fakultas yang unggul dan profesional di bidang pertanian berkelanjutan, dilandasi jiwa bela negara dan berwawasan global. Hingga saat ini, Fakultas Pertanian telah melahirkan lebih dari 8.000 sarjana dan magister yang kiprahnya banyak diakui di masyarakat. Fakultas Pertanian memiliki banyak fasilitas dan laboratorium yang dapat mendukung riset dan aktivitas belajar mahasiswa. Fasilitas dan laboratorium dilengkapi dengan teknologi terbaru, sehingga mahasiswa bisa mendapatkan keahlian yang sesuai dengan perkembangan zaman. Sistem administrasi Fakultas Pertanian terintegrasi secara online, sehingga mahasiswa mendapat pelayanan yang efektif dan efisien. Saat ini, Fakultas Pertanian UPN Veteran Yogyakarta mengelola 4 program studi, diantaranya Prodi Agroteknologi S1, Prodi Agribisnis S1, Prodi Ilmu Tanah S1, dan Prodi Magister Agribisnis S2. Semua telah diakreditasi, terutama untuk jurusan agribisnis dan agroteknologi sudah terakreditasi A. Dengan dukungan sarana-prasarana pembelajaran yang memadai dan dukungan sumber daya dosen serta tenaga kependidikan yang mumpuni, Fakultas Pertanian mendidik para mahasiswa dengan berbagai macam bahan maupun metode pembelajaran yang memperkaya pengalaman pembelajaran mahasiswa. Proses belajar dijalani sebagai langkah dasar untuk memperoleh pengetahuan sebagai bekal meraih masa depan yang lebih baik. Fakultas Pertanian telah mendapatkan berbagai penghargaan, diantaranya dan kerjasama, diantaranya komitmen Fakultas Pertanian untuk membekali mahasiswa dengan pengetahuan yang memadai untuk meraih masa depan yang lebih baik.
Fakultas Pertanian UPN Veteran Yogyakarta, bringing knowledge for a better future.
Saat kita sering meluangkan waktu yang Tanah UPN Veteran Yogyakarta berdiri tanggal 24 Agustus 1985 merupakan perguruan tinggi negeri di bawah Perguruan Tinggi Kedinasan Departemen Pertahanan Republik Indonesia. Pada tanggal 27 Februari 1995, Prodi Ilmu Tanah mendapat status disamakan di bawah Kopertis Wilayah 5. Sedangkan pada tanggal 11 Agustus 1998, Prodi Ilmu Tanah terakreditasi pertama mendapat nilai A di bawah Kopertis Wilayah 5. Sedangkan tanggal 3 Agustus 2008, Prodi Ilmu Tanah UPN Veteran Yogyakarta memperoleh kembali akreditasi dengan peringkat A. Sementara pada 11 Desember 2015, Prodi Ilmu Tanah UPN Veteran Yogyakarta diaktifkan kembali. Prodi Ilmu Tanah UPN Veteran Yogyakarta mempunyai visi menjadikan program studi ilmu tanah yang berdaya saing di bidang reklamasi lahan dan sistem informasi geografi untuk mendukung pertanian berkelanjutan yang berlandaskan jiwa bela negara pada tahun 2025. Untuk mencapai visi program studi ilmu tanah diperlukan 4 kata kunci. Pertama, reklamasi lahan. Kedua, sistem informasi geografi. Ketiga, pertanian berkelanjutan. Keempat, jiwa bela negara. Untuk mencapai kata kunci yang pertama, reklamasi lahan, diperlukan riset dan pengabdian masyarakat baik dosen dan mahasiswa, laboratorium sumber daya alam dan reklamasi, kuliah reklamasi, kerjasama dengan perusahaan tambang. Untuk mencapai kata kunci yang kedua, sistem informasi geografi, diperlukan laboratorium SIG, kuliah sistem informasi geografi, penelitian menggunakan metode SIG, geospasial, dan perusahaan pemetaan tambang. Untuk mencapai kata kunci yang ketiga, pertanian berkelanjutan, diperlukan kerjasama dengan perusahaan perkebunan, mata kuliah pertanian berkelanjutan, penelitian dan pengabdian masyarakat, pemanfaatan lahan marginal. Untuk mencapai kata kunci yang keempat, jiwa bela negara, diperlukan penggunaan kehidupan pengenalan kampus dengan jiwa bela negara, mata kuliah bela negara, dan Widya Matyasa, serta kerjasama dengan Angkatan Udara Republik Indonesia. Di program studi ilmu tanah menjadikan program studi ilmu tanah yang berdaya saing di bidang reklamasi lahan dan sistem informasi geografi untuk mendukung pertanian berkelanjutan yang berlandaskan jiwa bela negara pada tahun 2025. Dalam mencapai visi program studi ilmu tanah, diperlukan 4 kata kunci. Pertama, reklamasi lahan. Kata kunci kedua, sistem informasi geografi. Kata kunci ketiga, pertanian berkelanjutan. Sedangkan kata kunci yang keempat, berlandaskan jiwa bela negara.
Kami dari Babal Berbagi Kebaikan.
Good morning, ladies and gentlemen. Welcome to the international webinar of Soil Science Study Program, Faculty of Agriculture, Universitas Pembangunan Nasional Veteran, Yogyakarta. We would like to say thank you for register and become the participant of our webinar, Global Concern on Land Degradation and its Solution. Before we proceed the program today, we would like to express our sincere gratitude to Excellency Rector of Universitas Pembangunan Nasional Veteran Yogyakarta, honorable speakers from USA, Australia, Japan, and Indonesia, and all webinar attendees. My name is Liana Fatma Leslie Pratiwi. I will be your Master of Ceremony, and I would like to explain our agenda for today. The first is opening, and then singing national anthem of Indonesia. Welcome speech, speaker presentation, discussion, and then closing. Now, we will sing of national anthem of Indonesia and country defense song. Ladies and gentlemen, please place yourself.
Agama, ragam budaya serta
Thank you. Ladies and gentlemen, before we begin, I will read our rule webinar. First, list of attendance will be given 15 minutes in the chat column after the event takes place. Second, all webinar attendees can ask questions in Q&A column with format name institution _ name speaker _ short question. The last, certificate and presentation materials will be sent to attendees email 1 week after event. Now, our agenda is the opening remarks from Rector of Universitas Pembangunan Nasional Veteran Yogyakarta, Dr. Muhammad Irhas Effendi. Please, time is yours.
Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good morning, eminent scholar, honored guests, ladies and gentlemen, the participant of the webinar in Indonesia and neighboring countries. Good afternoon in Australia and good evening in the United States. It is great pleasure indeed for me to welcome you to our today international webinar on global concern and land degradation and its solution. This webinar is organized by the Soil Science Study Program, Faculty of Agriculture, UPN Veteran Yogyakarta. UPN Veteran Yogyakarta was established in 1958. It was reborn as a state university in 2014. Our university has been well known by programs in the field of earth sciences. We have very strong engineering programs in geology, mining, and petroleum, as well as related disciplines, such as soil science. Soil science study program in the Faculty of Agriculture is part of our strength in the field of earth sciences. Specifically, our soil science study program at our university concentrated on land reclamation and geographic information system. And currently we are in the process of opening a new master degree in land reclamation. Land reclamation has been becoming a critical issue worldwide. Globally, about 20% of agricultural lands, 30% forest, and 10% of grassland have been degraded. This issue certainly threatens billions of people on our planet now and in the future. In Indonesia, land degradation is sustainably high with a rate of more than 2 million hectares annually. There are 5 main causes that lead to land degradation, including 1, agriculture activities in general, such as annual and perennial crop and plantation, forestry, livestock, and aquaculture. 2, utilization of marginal land, such as peatlands, acid sulfate soils. 3, mining activities. 4, industrial waste. And 5, natural disaster, such as volcanic eruption, floods, landslides, forest fire, earthquakes, and tsunamis. These causes could decrease the quality of the component of our land resources and subsequent ecosystem goods and service. In addition, the current climate change has been projected to aggravate the situation. In most cases, degraded land become more vulnerable to extreme variation of climate elements, such temperature and rainfalls. Respected speaker, ladies and gentlemen, based on the described phenomena, it is obvious to us that land degradation is a very important global issue that needs to be scrutinized. We are happy today and tomorrow to discuss, exchange, and share knowledge and experiences in the issues of land degradation and measure and technologies to stop and combat land degradation and the further create sustainable land use in our earth. Therefore, on behalf of UPN Veteran Yogyakarta, I would like to take this opportunity to express my deep appreciation to Professor Aswar Maas from Universitas Gajah Mada University in Indonesia, Professor Thomas Baumgart from Federation University Victoria, Australia, Professor Naoto Matsue from Ehime University, Japan, and Professor Ali Munawar from UPN Veteran Yogyakarta, Indonesia. We will deliver their thoughts into this session. Professor Jeffrey S. Question from West Virginia University, USA. Professor Harry S. Utama from Louisiana State University, Baton Rouge, USA, and Professor Suwarji from Universitas Mataram, Indonesia. We will join to tomorrow's session. These respected speakers, interestingly, will represent almost all geographical origin of Earth side of the Earth. The southern hemisphere is represented by Australia. From the middle hemisphere, topics represented by Indonesia, and from the northern hemisphere, topic subtropic represented by Japan, and most north hemisphere represented by the United States. Beside the speaker will deliver land degradation from both perspectives, namely ecological aspect, such as wetlands and dryland ecosystem, major causes of land degradation, such as human-induced degradation, and technological aspect to reclaim degraded land using biotechnology and breeding approach and mineral matters. Distinguished speaker, ladies and gentlemen, before closing my speech, again, I would like to thank our respected speakers, guests, and all other participants for joining the webinar. Last but not least, I will also sincerely thanks and appreciate the committee of this international webinar for the hard work under the pressure of the current COVID-19 pandemic. I hope you will join and have the two most productive days of interesting and stimulating discussions. I sincerely wish that this webinar will be a great success, not only a great thing to share knowledge and experience, but also as a beginning of a long and fruitful cooperation and friendship among scientists and whoever devoted to the most important environmental issue worldwide, land degradation and its solution. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you to Dr. Muhammad Irhas Effendi. Excellencies, ladies and gentlemen, now we come to main agenda, plenary session, will be led by our moderator, Dr. Muhammad Nurkolis. First of all, allow me to introduce our moderator.
Thank you.
Okay. I will introduce our moderator, Dr. Muhammad Nurkolis. He worked as lecturer in Soil Science Study Program, Faculty of Agriculture, Universitas Pembangunan Nasional Veteran Yogyakarta. He got his bachelor degree from Universitas Gajah Mada, Indonesia. He got his master degree from Rikyus University, Japan. And he got his doctoral degree from Kagoshima University, Japan. Dr. Muhammad Nurkolis, please, time is yours.
Thank you very much, Miss Liana.
You're welcome.
Assalamualaikum warahmatullahi wabarakatuh. Your Excellencies, honored speakers, and all participants from US, Asia, Australia, and also Africa. Good morning for Asia, and good afternoon for Australia, and good night, yeah, from US and Africa. Welcome to our program of 2 days webinar on Wednesday and Tuesday, 26 and 27 August 2020. First of all, I am as a moderator, so let me deliver the urgency of the problems on land degradation that are caused by, yeah, at least 5 items that's already stated by the rector of Open Veteran Yogyakarta in welcoming remarks a moment ago. So land, which is a harmonious system, may function as habitat for all living things. If one or more of the land elements are degraded or even damaged, there will be no harmony in land system, so that it may not as function properly as habitat for living things, also for us. Open Veteran Jakarta has strength in the field of earth sciences regarding the global problems of land conditions, and also the surface of the earth that are increasingly degraded. We have concern on these problems that we catch them on webinar to discuss for finding solutions. The results of this webinar are expected to be an increase of our knowledge for us in terms of land degradation and alternative solution that we need to do. And also it may provide for our university plan to develop and open the master programs, especially in the field of land reclamation. So today we have 4 honorable speakers: Professor Azwar Maas, Professor Thomas Baumgartel, Professor Naoto Matsue, and Professor Ali Munawar. So they will deliver problems and reclamation of lowland in Indonesia, and then land degradation and reclamation in Australia, acid resistance of certain clays and zeolites, and then acid mine drainage and how to manage it. So in this webinar, we wish to invite speakers to deliver the presentation. Then it will be continued with a discussion. The time allocation for each speaker is 20 minutes. And then for the first honorable speaker, I would like to invite Professor Azwar Maas. Assalamualaikum, Professor Azwar Maas.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much. And first of all, may I briefly introduce to you the first speaker, Professor Azwar Maas from Department of Soil Science, Gadjah Mada University. Yeah, he is our teacher. Yeah, he graduated PhD degree with the specialization in wetland from Belgium. Yeah. And he is senior expert in the basic concepts of peatland restoration based on peat hydrological unit, and then health impacts of peat fires, and also basic concept of peat management supervision based on peat hydrological unit. Now, he will present the topics on degradation and reclamation of lowlands in Indonesia. So please Time is yours, Professor Aswar Maas, for 20 minutes.
Thank you, Mr. Moderator. Good morning, good afternoon, and good night for everybody. Depend on the situation on your position. Yeah, I would like to present as the same title that has been delivered to me about lowland degradation and reclamation. Please allow me to share the screen. Yeah. Okay. What is our tropical lowland? You know that lowland is environments can be formed in the depression between two main rivers. The water goes to the lowland, the depression, and bring the sedimentation. And later on, sedimentation occur in the reduction condition. And this situation can be in a freshwater environment and saline or brackish water environment. In the brackish and saline water environment, the pyrite soil will be formed. Yeah. So later on, after shallowing the accumulation of mineral soil, the plants start to grow, and then the plant also become a heterogeneous plant adapted to wet condition and become old and decay, falling down to the swamp, and the rate of sedimentation is higher than the rate of the decomposition. It means accumulation of the residue of the forest trees become more and more, and then we create what we call the pit soil. Normally, the situation of the pit soil is in the back swamp, and the leafy river still consists of mineral soil. So, in general, we have in Indonesia about 192 million hectare land, and then the total swampy land is about 34 million hectare, and the peatland that varies of information, but lastly, we still have only about 30.4 million hectare. And this peat land, we call that as hydrological unit that cover in between two rivers, upland and sea, and that we cover about 24 million hectare. So total lowland with mineral and pit depth with less than 50 centimeters is about 10.7 million hectare. As I mentioned before, sedimentation from the upper upland coming through erosion and lay down in the swampy land, mostly in final material as clay. Yeah, in some part we still have also with no clay, and then mostly it's a sand. Yeah, so most of our lowland in the mineral soil consists of pyritic material. This figure show you how we, let's say, as I mentioned, the swamp formation and the pit formation. And firstly, we create topogeneous pit. It means the pit still influenced by tidal movement or discharge of the river during the season. And then later on, if the pit going up and then no more affected by the tidal, we call that homogeneous pit. Normally, homogeneous pit is always stand up below, above the topogeneous pits. So if we mention about lowland is not degraded in the natural condition. Only human give the impact, the effect can this lowland can be degraded. You see here, this is one example of thick pit, and then you see along a lot of heterogeneous vegetation adapted to the wet condition, and then all three become decay and going down, and then bring the nutrient to the other neighboring young trees. Yeah, and the left side up, you see also meandering of the river, and then you see the plant is very good condition. If we compare to the pit on the top and the in the middle idea. So this is a closed system, but this situation only have a little impact to human life. So we should use the land to have a more benefit for human life. That the source of degradation actually. Yeah. So this is the illustration given to you. Pit dome in the middle, and then unripe soil material, reduction form, water storage in the pit dome, and then slow release of the water during no inflow, especially during dry season from the top of the pit. And then in the leafy oxidation, ripe and local settlement is there. Yeah. Before, let's say, in the first swampy development during the time of around 75 to 82, in Kalimantan, we create what we call that system, port system. Yeah, we don't touch the dome, because we know that dome will release water, and then we try to use the tidal movement for irrigation and drainage. Yeah, most of our system is on mineral soil or pit depth less than 1 meter actually. Yeah? And then we have problem for this leafy, because some of the leafy and then the beginning of the wax swamp is consists of pyritic material. So we introduced the water sharing design based on the pit hydrological unit. Yeah, you know, if we go to the swamp area, the peak thickness varies from less than 1 meter to up about 18 meters. But the horizontal is varies from 2 to 1 more than 100 kilometers. That's very flat actually. We cannot see the dome and the field. Only using the radar, for example, we know we have the dome. Yeah. In our resolution, if we conserve accordingly to the regulation, that 30% of the dome of the hydrological unit should be conserved, and then if we calculate our hydrological unit, 30%, and then we have 30-meter thick pit, and then we will have so huge of water, yeah, more than 10 times the total surface water stored in Indonesia. The problem is now, is the water still there? The answer is no. Yeah. So this is the example in Palalawan or Riau. We try to make a pit thickness survey detail, and then also covered by LiDAR. And you see here that the thickness of the pit here more than 12 meters, and then going down to the river. Yeah, and later on cracking from the top of the pit give us also the natural river. This river here is not upstream, not from upland, but from the top of the pit. So the water quality is brown, no mineral, and then consists of dilution of organic carbon in the bring the water become brownish. Yeah. Information during in some literature mention draining of 1 hectare peatland will emit about 20 metric ton of CO2 per hectare. Yeah. This happened during a few years after clearing. Land subsidence occur, including compaction, and the compaction can be 1 meter at the first year. Yeah. Opening the peatland and following by cultivation of, let's say, forestries for industry, there should be compaction, because in the natural condition, if we go walking in the pit natural condition, we can shrink. But in the cultivation, we can walk smoothly because of the compaction. Yeah. So this is the information about our burning in the 1997, and also the most dangerous thing is at last 3 years. Yeah. So because we have the dome pit, it means the source of the water only rain. The rain will leaching the decay of nutrient especially. So become thicker the pit, that become poor. Yeah. So basically, swampy land is less suitable for crop cultivation. Nutrient poor, parent material, anaerobic condition, mainly have thick pit, periodic ferrous depth. If they are competitive, they will disturb, and then they will release more problem. That problem can be solved by not at a short time, but reclamation of this material will take longer time than when we think. Yeah. This is the project of 1 million hectare, and you see the dome pit has been cutting by the canal, and then becomes loss of storage function, flood hazard, dryness, become rain fed, and very acid, toxic, hydrophobic, and compacted. Yeah. So how the way to reclaim? This is not a good way to reclaim. Yeah. Here the example, we have a pit mapping in the 1 million hectare, and then only suitable with low production of rice, for example, in the color of blue. Yeah. In reddish color is not suitable because the pit thickness is more than 7 or 6, more than 7 meter actually. Yeah. Here, lastly, I think during the 3 months before, our government start to worry about our food. So government asks how to reclaim again, to use again the 1 million hectare project, and then this already reclaimed for more than 20 years. Yeah. Later on, for the left side, I tried to pull up the one rice, and then this rice, the rooting zone is very deep. Yeah, the periodic layer is below 50 centimeter already. So we hope that we can get twice planting rice for 1 year, and then we hope the production will be above 7 ton per hectare. And then the middle one, This is the water condition not so good because it's so far from the river, and the periodic oxidation is occurred, and we see the plant is not so good. And in the right side, in the right side also we try to intensify more production and then more planting time for 1 year. We do hope that we can have at least double of the production during next 3 to 4 years. Yeah. Here our regulation mentioned about our groundwater level is less than 4. In this picture, the canal water is about 30 centimeter. So it's mean the groundwater level is less than 30. But if the surface of the land is bare, is subject to fire as well. Even the groundwater is less than 0.4 meter. So it means in the future, don't let the surface of the pit become no cover crop. This is illustration. You see the different color of the water. Black color is coming from the pit dome, and then yellowish color coming from the river. So they can mix each other. So it means if they mix each other and then they create a turbulencing, and then the soft organic matter will release become CO2. So this potential liberation of CO2 to the atmosphere coming from the creating drainage in the pit soil. Yeah. So how about the future? Illegal logging should be terminated, not allowed again. Yeah. But how? Canalization, no matter in the in the function of conservation should be closed. Yeah. Conversion not allow for monocropping, because monocropping they don't deliver nutrient, but they need nutrient. Yeah. Drainage, fire, decrease the biodiversity, and then no more deforestation. Keep the pit in the moist solution, and also very good if the periodic material we use that for let's say paddy irrigated form, because the reduced condition will reduce also the oxidation of the period become very acid. I think this is my last presentation. You see here the turbulence of the water bring up the bulbing, and inside the bulbing is CO2. Thank you for your attention. Waalaikumsalam warahmatullahi wabarakatuh. Yeah.
Waalaikumsalam warahmatullahi wabarakatuh. Very nice, very interesting presentation from Professor Azwar Maas that I think all attendees can easily catch. Yeah, the material that already delivered by Professor Azwar Maas. Yeah. Okay. Thank you very much once again, Professor Azwar Maas. Yes, and
I cannot how to release my presentation. Please, host, help me.
Oh, okay. Please, technician, to stop the presentation. Okay.
Okay.
Yeah. You're welcome. Okay. Then for the second presentation, I will invite Honorable Speaker Professor Thomas Baumgartel, PhD. Good afternoon, Professor Thomas. Hello, good afternoon.
Good afternoon.
Yeah, very nice time now, I think. Yeah, yes. Professor Thomas, he is a professor and director of Geotechnical and Hydrological Engineering Research Group, GHERG in Federal University Australia from 2018. He earned many awards from many institutions in Germany, and then also president of Australian Society of Cell Science in Queensland branch, and also many positions that he had achieved that we are not able to mention all. So Professor Thomas will present the topics on the land degradation and reclamation in Australia, selected experiences from agriculture and mining. So please, Professor Thomas, time is yours, 20 minutes.
Thank you, Dr. Nokolis, and thank you very much for the nice introduction. I'll try to share my presentation. And I hope you can hear me well.
Okay.
Just let me know if there is a problem.
Very well. Yeah.
Yes, yeah, thank you for the invitation to present an Australian view, your southern neighbor, where conditions are quite a bit different than in Indonesia. Just a brief overview of the content of what I would like to present. A brief introduction referring to some of the main factors contributing to degradation, which are typical for the Australian context. Then present a few example cases of degradation and reclamation or rehabilitation in agriculture and likewise in mining, and then finish with a few thoughts on consequences and conclusion. Now, land degradation from a definition point of view refers to chemical and biophysical changes in land that can be measured as a decline in quantity and quality of what, from an agricultural, but also from a natural point of view, quantity. Agricultural land may be linked to a reduction in the productive capacity of land and its economic value. Apart from the biotic and abiotic degradation, which we are commonly experiencing and which we probably discuss greatly in this seminar, there's also a cultural degradation. And above all, the indigenous population in Australia is probably is quite affected or has been often affected by this kind of degradation. In general, 2/3 of Australian agricultural land is considered as degraded, and I'll make another comment later on that. Mining is probably a bit of a different story, because mining and degradation in mining probably has to be viewed as a consequence of unsuccessful rehabilitation. And mining as such, and the disturbance may not be viewed as degradation as such, but the consequences which are resulting from mining activities, of course, have major outcomes and consequences. What is quite important to understand and to make the quantification or the assessment of the degree of land degradation important is the definition of a baseline, whether that's in agriculture or in mining. And that is often, the baseline is quite important because it does present a reference, but it's often very difficult as well to actually set parameters and values behind a baseline. Now, there are some typical Australian typical factors which are helping or contributing to degradation. And those challenges in the Australian context are the geology and soils, which we usually find in Australia. Australia, as you know, is a very old continent. That means weathering processes have occurred over very long periods of times. Soils which are built from those weathering processes have quite as an uncommon feature of those soils is that salinity levels are quite high, and salinity levels are increasing with increasing depth. So on the surface, soils may be suitable for plant growth, but with depth we have an increase of salinity. And that is largely based on the type of geology which we find, which is a very salt-enriched sedimentary rock geology in large parts of Australia. Soils which are generated or have developed out of weathering processes of these types of strata are often sodic or saline. Another factor which is contributing to degradation and quite typical, I think, in the Australian context is the climate. Climate can be viewed from the point of view of annual averages, but annual averages don't often tell the real story. What is more important, apart from categorizing annual characteristics, is to include seasonal characteristics and in general the degree of variability of weather events. Now, rainfall distribution in Australia, as you can see, is ranges across a wide range from 0 or 50 millimeters to over 3,000 millimeters. High rainfall is only along the coastline, mainly in the east and in the north. But very quickly, when you move inland towards the center of Australia, the rainfall becomes relatively low, and 300, 400, 500 kilometers inland from the coast, the annual rainfall is down to 500, 400, 300 millimeters. This map shows the annual rainfall of various years across Australia. The more pronounced the color is, either red or blue, means that these are extreme events based on an average value, or the other way around. If that year appears very uniform and in white color, we are very close to average values. Just looking at those 40 years of analysis, you can see that there is quite a lot of red and blue colors, which means that rainfall can be either very deficient or can be very abundant. And I've experienced that myself at a location where within 4 years, we experienced annual rainfall of 85 millimeters in 1 year, and over 900 millimeters alone for the wet season just 4 years later. What is typical for Australia as well is the seasonality of wet and dry seasons, where you have no rain for 4 or 5 months in large parts of Australia, and then abundant rain over the rest of the year. The consequence is that meaningful agriculture is really restricted to the East Coast, and the high rainfall zone, and then adjoined to that, what is called the wheat sheep zone, and the rest of therefore the large parts of Australia is considered as rangeland, where you may have cattle grazing. The main causes for land degradation in the Australian context is soil erosion, soil salinity, soil acidity and soil contamination through anthropogenic activities. Water erosion can either cause sheet erosion, or in this example, I've added a photo of typical erosional processes which lead to gully erosion. Another important type of erosion is wind erosion. Due to the very flat characteristic topography of the Australian continent and certain weather patterns, large parts of soil can be mobilized and move across the whole continent with quite devastating effects for some farming areas. Another important factor for degradation is salinity. And we distinguish here between primary salinity, that means the inherent salt content of soils is having a negative effect. But we also find secondary salinity, which is mainly human induced. So through the inappropriate use of land or either by irrigation with water, which contains salts, or through what is called dryland salinity, which is a change of the management of land away from forestry use to cropping, and that leads to an increase of the groundwater level. Groundwater level is getting into contact through capillary rise to the surface. That means there is a hydrologic connection, and that is then transporting salts to the surface and causing negative outcomes. Rehabilitation of land which is sensitive to either water erosion, surface erosion, or even wind erosion has started many decades ago in Australia and is still being implemented continuously. And contour banks is one of those ways to manage water flow, surface runoff, and control that runoff in a way to prevent any mobilization of material. This example is from guidelines from the Queensland government, which is available for every farmer and is used to support any decision-making process to improve the use of land without causing degradation. This is a historic photo, maybe 40, 50 years old, where contouring has been implemented on land. And as you can see, a lot of experience had to be created to optimize such contouring of land, as those contour distances in that example have been too wide, and even despite contouring, there's still erosion happening. What helps as well to manage degradation is just the general agricultural practice. And in the 1980s, a lot of research has gone into understanding the optimal management of cropping land, and zero tillage, as you can see, has been found as creating a huge advantage over other management practices to minimize soil loss at similar runoff rates. Also, farming practice by implementing, for example, strip cropping. That means there's always one crop on the land over the period of a year, is supporting or is reducing the risk of any negative outcomes, and therefore minimizing degradation. In general, agricultural practice has changed over the years. through advising farmers and convincing farmers, and over 15, 20 years, cropping land, which was managed through reduced tillage, has now changed to cropping land where almost all of the cropping land is either being managed through reduced tillage or through no tillage. Now, a few thoughts around rehabilitation and degradation in mining. Mining is a very different beast compared to agriculture, as the impacts are much more severe, however localized, and the tasks, the demands for rehabilitation are on a very different scale. Here on the left, this photo shows a tailings dam, which is about 12 kilometers long. And here, that's in Australia, and here on the right, that's a mine site in the US with just enormous waste rock dumps. Now, rehabilitation in mining can be quite challenging, and this photo shows a rehabilitated waste rock dump of a coal mine with sedimentary rock, often saline and sodic, and therefore high dispersive, tending to erosion, and that the outcome of the rehabilitation has to be considered as unsuccessful. As you can see, there are a lot of signs of surface erosion and gully erosion, and all this rehabilitated land has to be rehabilitated again. What is important for rehabilitation, though, is to really understand the material properties of the substrates which are used to carry out rehabilitation. This is an example. You look at a slope of a waste rock dump, which has been rehabilitated with available soil material, which was quite sodic. And on the left, the same material was used. However, it was covered with rocks. And as you can see on the right, the rehabilitation was unsuccessful. On the left, the rock cladding allowed the establishment of vegetation, and it is a very different success story. Now, what I mean by understanding material properties does even apply for the cladding. Not every rock which you find is suitable to cover the rehabilitation site. A study has been done which was investigating the potential of degradation of rocks which were found as part of the geology. And yeah, on top you can see here those 4 example rocks which have been wetted and dried over 10 times. And what you can see is that over 10 times the materials have changed, disintegrated either completely or partially, and only sandstone was a type of rock which remained competent and actually suitable for rehabilitation, and by applying that cladding concept. Important as well for achieving successful rehabilitation is understanding the temporal dynamic through external factors. Here, there is a rehabilitated site where the salinity levels have been measured as electrical conductivity over depth. And what an analysis showed by incorporating or understanding the rainfall regime over those years, it showed that the drier the year, the higher the salt levels were moving towards the surface, and the wetter the year, the further down the salt levels were moving. That means if we are assessing the success of rehabilitation, we need to be very careful often as well to really understand what are the conditions under which we are taking the measurements and assessment. The success in rehabilitation and reclamation requires, as I said, understanding processes which determine what a stable landform will have to look like. That includes understanding the hydrology, the mechanical stability, the chemical, geochemical stability, and the biological contribution. And on top of that, we also have climate or climate change, which we are experiencing currently. Briefly, I would like to give you an idea how that knowledge can be applied. This is an example for the cover design for waste rock dumps, which may illustrate how to improve rehabilitation.
1 minute more, please.
Okay. On the left, you can see waste rock material, which is consisting of very porous, very coarse rocks. That material is very typically, has very coarse pores. That means rain events can very quickly be distributed over depth. We adapted a cover design, which was taking that into account, and we added a hydraulic barrier on a sloped cover to incorporate this phenomenon of preferential water flow. The preferential water flow is not necessarily applicable for any environment. You need to have the right or the wrong quotation marks rainfall distribution, but it's a very important component for understanding which type of cover can be applied. Now, all this knowledge can be used to optimize the design of landforms. And there are tools, meanwhile, around which are helping to shape the land, to better build landforms, which can deal with the external factors, inputs in a much better way than what we have experienced in the past. Like here, it's an example of a rehabilitation of a quarry. In the past, we probably would have only would have gone this path where we straight lines, optimization of the deposition of waste material was in the foreground, whereas in the future we should rather follow rebuilding landforms which are more adapted to more stable conditions. And as a last thought, what we need to do, though, is to really understand how those landforms develop. We need to be clear that in the beginning, there will always be a very high level of reactivity, of change, of whatever we are creating. And this change will change over time. And what we need to learn is to understand what the trajectory of this change is. Because in the initial phase of rehabilitation, that's what we are usually experiencing in our lifetime partly, and we cannot often look really forward what the final outcome will be. Conclusions: land degradation is a problem which can be managed. Addressing degradation problems requires a multidisciplinary approach. There is no one-size-fits-all solution to many issues. Understanding the trajectory to reach an equilibrium is key, and that requires monitoring, and can really emphasize that point. And we need time to really understand how the system which we are rehabilitating or rebuilding will perform over time. Thank you.
Thank you very much, Professor Thomas Baumgartel. Very nice presentation and very important things, how to manage the land degradation and how to make agriculture and also mining area. Thank you very much. Yeah.
Thank you.
And then now we'll continue for the third presenters, honorable speakers, Professor Naoto Matsue. Now, good afternoon, Professor Matsue. Hello.
Good afternoon.
Yeah, good afternoon. I think there's lunch time for you. So
Yes.
I'm sorry we disturbed your lunch time. Okay. Professor Matsue is professor in Department of Environmental Conservation, Faculty of Agriculture, Ehime University from 2014. He finished in Agriculture Faculty, Kyushu University, 1991. For his works, many papers were published in the reputational journals, especially in new or nanomaterials for remediation for contaminated soils and also water. So I think the topics for the present is acid resistance of clay and zeolite affected by their chemical composition and structure. I think this topic is very important thing, how to manage the clay, especially for the in the acid environment, and also zeolite. I think many research for this materials, especially clays and also zeolites from Professor Matsue. And now, please, 20 minutes times for yours. Okay.
Now, okay.
Okay, please.
My slide, okay.
Okay.
Good afternoon, everyone. This is
Good afternoon.
Naoto Matsue. I would like to show you two topics. One is chemical composition and structure affecting acid resistance of clays and zeolites. In the chemical degradation of solids, dissolution at high or low pH, and pollution by such as heavy metals may occur. Then in this presentation, low pH effect is shown. The second topic is not so related to land degradation, but the application or utilization of acid resistance of zeolites and clays. I would like to introduce sanitizing drinking water by using proton-retaining zeolites and clays. At first, chemical composition and structure affecting acid resistance. Clays and zeolites have isomorphous substitution from silicon to aluminum or aluminum to magnesium. This produces negative charges that can absorb cations and protons. In case of clays, the position of the substitution determines acid resistance. In case of zeolites, aluminum to silicon ratio determines the acid resistance. This figure shows the side structure, side B of 2-to-1 type clay mineral, showing the substitution at both sheets, in octahedral sheets and tetrahedral sheets. So usually, the substitution can occur on the both sides. When occurred at tetrahedral sheet, the outer surface, this aluminum replaces silicon. As a result, the formation of SiOl bonding occur. SiOl bonding here. This is also shows SiOl bonding and having negative charge around here. This bonding oxygen has very high affinity to H plus and forms SiOH bonding. The formation of this bonding causes dissolution of two-to-unclay minerals. Two-to-unclay minerals at low pH dissolve here, from here. On the other hand, at high pH, the dissolution by OH minus occur at the edge of the two-to-one layer silicate. This type of substitution at tetrahedral layers is shown by vermiculite, biederite, and saponite. In contrast, for octahedral case, magnesium replaces aluminum. Then MgO bonding is formed. And of course, no formation of SiOl bonding. This bonding, MgOl, and also this oxygen bind to silicon. Then, of course, has no affinity to proton, and also inside of the structure. And also, if no substitution at tetrahedral sheet, the surface is composed of SiOl, only SiOl, SiOl. This bonding has no affinity to proton. Momonite is a typical clay of this type. Because no affinity to proton, acid resistant. Momonite is acid resistant as compared to vermiculite, biederite. So this is the explanation for clays acid resistant. The position of the isomorphous substitution determines the acid resistance. Next, for zeolites, in conclusion, SiL ratio of the structure determines acid resistance. Zeolites has three-dimensional structure, aluminosilicates composed of SiOl bonding, L or Si, aluminosilicate. If aluminum content is low, CC, cation exchange capacity, is low. This type of zeolites are molybdenite clinochloride. In Indonesia, you have much natural clinochloride. For high aluminum content zeolites, CC is very high. And this type of zeolites are Linde type A or A4 or fortified X. Is a typical high CC zeolite. The acid resistance is very high for low SIL zeolite because the oxygen exposed has low affinity for protein. For high ASI zeolite, the oxygen on the surface has high affinity for proton. Then this O become OH and dissolve the structure, similar to the case of 2-to-1 type clay mineral. High affinity or bonding with proton cause dissolution. Then high CC zeolite, A4 for the site X, has low acid resistance. In contrast, low CC zeolite, such as molybdenite, fluorite, has high acid resistance. The next slide shows the example. This plot shows the result of this experiment. For sodium saturated sample, proton was added as nitric acid. After shaking, we measured the sodium remaining on the surface. In this case, 2 sodium is released and 8 sodium remaining. So the vertical is the sodium ion remaining, and the horizontal is the pH. With adding nitric acid, in case of A4, pH decrease, and also the amount of sodium retained decrease. It means sodium is released and proton absorbed. Surprisingly, around pH 8, the absorption of proton occur for high CC zeolite. In contrast, for molybdenite with low CC, with low aluminum content, with the addition of nitric acid, pH of the solution decrease, but no release of sodium. The release of sodium occur around pH 4. This means molybdenite has low affinity for proton. In other words, molybdenite is a strong acid. A4 is a weak acid. Molybdenite, no dissolution, even at pH 2.4 here. No dissolution was observed. This means molybdenite can retain proton and release the proton to water easily. Then I applied this phenomenon to killing E. coli in water. This is the second topic, sanitizing drinking water by proton retaining zeolite. Proton released from proton molybdenite can kill E. coli. This is the Japanese girl going to school. She going to take drinking water. So I would like to develop simple tools for the people in rural area. Also, many knowledge accumulated by scientists, including soil scientists, the knowledge is not utilized in rural areas because construction of tap water is very difficult. And even machine is very difficult to use in such a rural area. Then I think simple tools, easy to use, cheap one is very useful for sanitizing water. How to kill E. coli? Usually boiling hypochlorite is used. Here I tested changing pH, low pH, and kappa. Natural mordenite was embedded on unwoven fabrics, and proton kappa retained is released to water to kill E. coli. Preparation is very simple. Kitchen filter, natural mordenite powder, heating, obtain embedded sheet. Then wash with nitric acid to obtain HMEF, and wash with mixture of nitric acid and kappa nitrate to obtain HCuMEF. This is outline of this experiment. E. coli plus sheet and pH decrease, and kappa released. The level is lower than 1 ppm. This is the result for blank. Blank E. coli increase with time until 24 hours. When we added proton mordenite sheet, drop 1 hour, 8 hours, after 16 hours become 0. By using proton kappa sheet, the effect is accelerated, and after 8 hours, no E. coli was found. So this is not so important. Important is also clay mineral such as montmorillonite having high acid resistance can also be used in the place of mordenite. In addition to E. coli sanitization, the zeolite sheet can be used to clean up water contaminated by heavy metals. Our experiment showed that high concentration of lead in water was removed by A4 embedded sheet in 30 seconds, become 0. So as such, zeolite embedded sheet can be used to removal of heavy metals in the environment easily, because after cleaning up, the sheet can be separated, removed by hand very easy. And also in this case, montmorillonite has high affinity to heavy metals. Then montmorillonite can be used in the place of A4 zeolite, because A4 zeolite are very expensive. This is the end of my presentation. Thank you very much.
Thank you very much, Professor Naoto Matsue. So you talk firstly about the basic sciences in clay mineralogy, but after this, by your technology, you can give us appropriate technology that can be used in the rural area, that how people, especially for the remote and the poor people, how to purify the water that can be used for the daily uses. Very thank you for Professor Matsui.
Thank you very much.
Yeah. Okay. For the fourth honorable speakers, the last but not least, Professor Ali Munawar. Good morning, Professor Ali Munawar. Good morning. Yes. So he also host of this webinar. And then firstly, I will deliver a brief information about Professor Ali Munawar. Professor Ali Munawar is professor in Soil Science Study Program, Universitas Pembangunan Nasional Veteran Yogyakarta. He graduated from Gajah Mada for the engineer, and then master program, and also a PhD in Kentucky University in US. Now, many research, especially from him, about the coal mining environment, especially in the coal mining environment. And now, I think, yeah, he also a consultant in Ministry of Environment and Forestry, and also Food and Food Agriculture Organization Indonesian Office. Many papers also published from journals and seminar proceedings. And now we invite Professor Ali to present the topic about the acid mine drainage, a threat from mining sites in Indonesia and how to manage it. Times for yours, 20 minutes, Professor Ali.
Thank you, Prof. Nurholis. Let me share my slide, please. Okay. Is it clear, everybody?
Yes.
My side, well, my presentations today is acid mine drainage, a threat from mine sites in Indonesia and how to manage it. My outline is one introduction, how important the mines in Indonesia, acid mine drainage, and I'll talk a little bit about how to manage from my short experience in the field. Well, I think everybody knows that Indonesia is very important producer of different kinds of mine products. So mine is very important in national economy of our country. Mine is just like a coin with two faces. One face, it gives so many benefits to us, like we live in the modern society. Like now, we almost cannot avoid the benefits of the mine. What we have, to wear, like our laptop, our watch, everything what we work our deal to daily is associated with mine products. However, the other side of the coin is that mine causes environmental degradation. Today, I'm going to talk about acid mine drainage. It's known well as the most serious threat from mine areas. Here is Indonesia. We have a big coal productions. We are in the 7 or 6 in the world as a producer as well as a exporter. Mainly coal resource we find in Sumatra Islands and Kalimantan, or we call it Borneo, and several other places. Coal mines in Indonesia varies from very small, like family mines, to very big, like we in Bengkulu. Like in Bengkulu, we have various very spotty mine area over there. We have various size of is in Kalimantan. For example, this is a raw coal in East Kalimantan, and the large mine like Bukit Asam we found in Sumatra. So we have various kinds of coal mines in Indonesia. We also have mineral source that we are mining, like precious metals, golds, and other different kinds of minerals. And we also have these mines in several areas, Sumatra, Kalimantan, as well as other islands out of these 2 biggest islands in Indonesia. Gold mine in Indonesia, like coal mine, we have a various level of size of the gold mines, like people mine, what we call a small scale mines, gold mine in different areas of Indonesia. Like I show you, this is in Bengkulu, in the first part of Sumatra Island. This one is a very famous area of small scale mine we found in Lebong area. We also have various in coal mines in Kalimantan. Like this was, it is Indomuro in Kalimantan. And we have a giant, like everybody knows, of the gold mine in Papua, PT Freeport, Indonesia, which is well known as gold as well as copper productions in the world. What is acid mine drainage? By definition, acid mine drainage is acidic water with high acidity, and is often characterized by pH value lower than 5 as a result of oxidations of sulfide minerals with air or the presence of water containing oxygen. Actually, acid mine drainage is not a new issue because it has been observed by a priest who is Diego Delgado in Rio Tinto mine district in Spain in the age of the 16th, the 1556. So it's old stuff, but it's still very popular today. Acid mine drainage is formed from sulfide minerals, like in here, as an example is pyrites. If pyrites is exposed to oxygen and water, is going to dissolve and oxidize, forming sulfuric acid and releases ferrous iron. And then the ferrous iron is oxidized, forming very hydroxide. And the very iron is able to oxidize again the pyrites under anoxic conditions and release sulfuric acid, so that the whole of the reactions produce low pH or high acidity and high dissolved metal, because under very low, sometimes extremely low, every metal can be dissolved. This is how acid mine drainage appearance. So sometimes we falsely judge the acid mine drainage always yellow or red. But in the beginning, actually, before there is a naturalization process, acid mine drainage can be very clean. So do not judge from the color. The color doesn't tell sometimes what it is, what is inside, what is the content of that clear water. This is different kind of appearance or of acid mine drainage. I found it in Iberian Bight belts in Spain, which has pH extremely low from 2.6 to 0.9. We also found it in some good mines, like this is an example of seepage acid mine drainage coming from embankment of tailings in Papua. MD forming factor is principally like the reactions, as I saw, that sulfide minerals is the basic component. So if there is a sulfide minerals, there is a potential to produce acid mine drainage. If there is oxygen and water, this condition, it is going to, under this condition, sulfide mineral will oxidize. And of course, there are seasonal due to climate elements. Oh, there are some microorganism which is very resistant to a very acidic condition. We call it Aciditobacillus viroxidans. They live in a very acidic condition that they can help and to be catalyst in acid mine drainage formation. This is sulfide minerals generally found in mine sites. Like pyrite is the most abundant sulfide minerals, and then followed by other sulfides minerals. Sulfide minerals and IMD of formation. Well, mine activities just started by removal and exposure of rock or overburden containing sulfide minerals such as ferrite to surface of the earth. That's what this is the materials that we remove from the ground if we are mining. You can see various kind of stone, and also you can see how mining leave pits which also expose the wall so that acid mine drainage can form. Mine activities such as coal washing, coal crushing, and also all processing and waste, they can generate acid mine drainage. Like this is an iron sands and tin, and this is tailings, and this is coal crushing and coal washing. They can release sulfide minerals which can oxidize, then form acid mine drainage. Where to find acid mine drainage? We can easily find in mine sump or pits, runoff in the mine site, drainage system, go to the pond and creeks, seepage of in the area of mines. Like this from runoff. This one I was there in 2007. The runoff water pH is about 2.3, and there are also pits, and there's several other places that we can find acid mine and drainage. This is just some of characteristic of acid mine drainage that I found in several companies that I associated with, like Bukit Asam in Sumatra. The main metal that we found there are aluminum, iron, and manganese. They're all above the threshold of that should be followed. It's very similar that we found in South PTBR, Bukit Asam, South Sumatra. The pH of various, where there's from 4 pits in the similar area, but different lithology. So the pH also varies from 2.6 in what BB is Bangko Barat, it is mining unit, and then we have Airlaya and MTBO, which has different pH, and also the the concentration of dissolved metals. Yeah? Manganese and iron are two most important metals in the area. We moved to East Kalimantan with Borokol. We found that this area, especially in the Lati mining operation, this area is dominated by potentially acid-forming materials. 80 to 20% of the area. So that's why this area is very well known as a problems area, in which pH is very low and metal concentrations, especially manganese and iron and aluminum, is high, even though there's variations among the sites. This is a potential threat from gold mine. I took it from Tabarima 2020, but this is still in the active tailings. Some of these seepage contain sediment that potentially toxic to water life. Now, in summary, environmental impact of acid mine drainage is one is ecosystem degradation because of extremely low to low pH or high acidity, high dissolved sulfate, and high dissolved metal concentration. Surface water and groundwater pollution, harmful to aquatic organisms, harmful to crops and other terrain organisms, and also damage to infrastructure corrosion like bridge and dam. So acid mine drainage characteristics vary among site to site. So there are some mines that do not produce acid mine drainage. There are some produce moderate acid mine drainage. There are mines that produce very extreme problems. Now, also seasonal effect also affects how the danger of acid mine drainage. In most areas of Indonesia, like in Sumatra, in Kalimantan, which have high rainfall, so it's easily transport acid mine drainage widely spread and pollute downstream areas. So it's quite different from Australia areas where they have a very low rainfall. So the distribution or the spreads of the acid mine drainage is not as a big problem as we found in Indonesia. Again, acid mine drainage as a threat. One is formed. So when the sulfide mineral is oxidized, it will never stop until the sources sulfide minerals completely weathered. It can last for years, and even ages. So that is very important to to be aware of this. So therefore, I would say that acid mine drainage is a threat in the past, was a threat in the past, a threat now, and threat in the future. Therefore, we have to consider it very well. In the past, in 1556, Diego Delgado's observation, he observed that pilot oxidation lead to formations of IMD products. Fa or iron dissolved in IMD water. Iron hydrolysis and form iron-rich cement in sediment. Acid mine drainage toxic to fish and other aquatic organisms. And simple experiment can reveal acid mine drainage ecotoxicity. So now in the future threat, that I said that if it is formed, then it always long-lasting form until the sulfide mineral is gone. See, so the historic mines told us about that. The current increasing mine activity, it means that acid mine drainage as a legacy problem for the next generation. So the future threat. So how to manage acid mine drainage? Acid mine drainage management is a must, and it is multidisciplinary approach to combat acid mine drainage. We have to approach preventive and curative or corrective approach. Preventive is always better than treatment. The basic principle of curative approach is to avoid acid mine drainage formation by controlling acid mine drainage forming factors, and to protect sulfide minerals from oxygen and water contact. This is usually done by acid-base accounting to differentiate material that is potentially forming material, acid-forming material, and non-acid-forming materials. This is what a company can do. This is practice that is being done from South Sumatra. So what we have to do is, this is for preventive. We have to isolate path under the cover of NAF so that oxygen and water cannot touch, cannot contact with the path, so that acid mine drainage can be avoided. So if path and much bigger than NAF, then we're going to have acid mine drainage. But if we have NAF much more than path, then less acid mine. This is encapsulation practice in Kalimantan. It is also in Kalimantan. Corrective principle is to reduce acidity and dissolve metal concentration. Can be active by addition of alkaline materials to increase pH and to dissolve, to decrease, to reduce dissolve metals. Passive treatment like open limestone drain, anoxic limestone drain, aerobic and anaerobic wetland. We have developed such constructed wetland in East Kalimantan. So the new thing that we probably need to develop is phytoremediation, how to use plants to extract dissolved metals from acid mine drainage. A conclusion is the acid mine drainage formation has been and continuously formed in mine site in Indonesia. So acid mine drainage formation takes place long lasting as long as sulfide mineral is there, it's gonna takes place for years. And IMD has been a serious threat in the past, now, and the future. Therefore, acid mine drainage management is a must, started even before mining is on operation. Thank you very much.
Thank you very much, Professor Ali Munawars, that already deliver about the acid main drainage. Yeah. Now, I think for honor speakers already presented their topics, and now we move to the question and answer or discussion. Here, we will divide to circulars, yeah. And then I think there are many questions that already delivered by attendees with the question and answer. And now we have 4 questions from selected attendees. First, from Kukuh Setiawan from Universitas Lampung, Indonesia. The question for Professor Azwar Maas. The question is how to maintain the water in order not to be subsidence in the pit area. It is okay for Professor Azwar Maas. Hello. Hello, okay. Professor. Yeah, okay. Yeah, after this, we will collect for questions. After this, we ask the presenters. And the second questions from Veronica from Mozambique, Lorio University. Yeah, because there is also attendees from Africa, from Mozambique. The question to Professor Thomas, the question is, I would like to know if there are sustainable and easy methods for conservation or recovering the land in the mining zones. Okay, the questions for Professor Thomas, correct?
Yes.
Yes, okay. And then the third questions from Japan, from Erna Mayasari. The questions is for Professor Matsue. The question is, how could we predict acid resistance through the 3-dimensional structure of natural and synthetic zeolites? Yeah. How could we predict acid resistance through the 3-dimensional structure of natural and synthetic zeolites? Yeah. And then how could we know high and low acid resistance just from 3-dimensional structure of zeolites? Okay, for yeah, okay. And then for Professor Ali Munawar, there is a question. You know that UPN Veteran Jakarta will open the master program. So what is the concentration of the postgraduate or master program? And then whether from the aspects of lecturers, laboratories, and collaboration with users, like our stakeholders, have supported the program. Yeah. So what is the concentration of the master program? And then whether from aspect of lecturers, laboratories, and also collaboration with users or stakeholders have supported the program. Okay. So first, we ask Professor Ali Munawar to answer the question from Mr. Kukuh Setiawan from Universitas Lampung, Indonesia. Please, Professor Azwar.
Yeah, to keep the water table is most important close to the surface. And then let's try the surface not to be bare. Should be planted by, let's say, cover crop. Yeah, this is the way to reduce subsidence. Anyway, we may reduce the subsidence, but we cannot avoid subsidence if the original forest has been converted to the utilization. Yeah, because subsidence anyway having microbial activity at the surface, aerobic condition, and then that takes, and also the source of nutrient from the decay of the remnant of trees or at the surface, especially leaf, for example. This is fast decay and then liberate nutrient, and then later on the pit will be also oxidized by activity of microbial. Yeah, thank you.
Okay, thank you very much. I think so clear for this answer. And then the second, I will ask Professor Thomas from Australia. The question from Veronica, yeah, from Mozambique, Lorio University. Please,
thank you.
Professor.
Thank you, and thanks for the interesting question. If we, yeah, the answer is probably there is no easy method. What is important to understand is if we are digging into the ground, if we are changing the environment, we are changing the equilibrium that environment has been in. If we are rebuilding something, there is the system is not in equilibrium. That will only happen over time, and that can be a short time, that can be a long time. A new equilibrium has to be built either from a mechanical point of view, that material is consolidating and becoming stable. From a chemical point of view, we have material is suddenly available for oxidation processes, which didn't happen before, which is causing a different type of weathering and different outcomes as we might experience from the land next door and undisturbed. So what is really important is to understand the material properties as much as possible and what you would like to achieve with that. Now, often there is not the potential or the complexity of what you want to achieve is so big that you may not be able to really understand all the details of what you would need to understand. And where there is a lot of value, though, to create an understanding of what can be best practice and how one can avoid any mishaps or misplanning is to communicate with others who have done something similar and to try to learn from others what has worked and what hasn't worked. And while you're getting that understanding on the principles of what does work and what doesn't work, you can then at the same time create experience and knowledge by detailed understanding of properties of the materials and performances of your ecosystem and all these factors which play in. You can create that confidence over time to build a stable, sustainable, rehabilitated mine. But it needs, yeah, as I said, it's not easy and it needs experience internal or external, and it needs, in many cases, it needs time. Thank
Okay.
you.
Okay, thank you very much, Professor Thomas. And then I will ask Professor Matsue for the question from Japan, from Ennamayasari. Please.
Can I share my PowerPoint file?
Yes.
I want to
Fine.
use by slide.
Okay, please.
So this chart shows the pH begin to absorb proton. But so this is very difficult to explain now, but pH is about 8. So the horizontal is the SIA ratio. In my presentation, SI ratio. But anyway, the acid proton selectivity is mainly correlated to the composition of the pore structure, although this is one type of zeolite structure. This is another type of zeolite structure. Another type and another type. The types of the three-dimensional structure is different, but the proton affinity and acid resistance is mainly related to the composition of the pore structure. So then the answer is the factor determining the acid resistance is the pore ratio of silicon and aluminum of the zeolite. This is my answer.
Okay. Thank you, Professor Matsue, for the explanation. And then I would like to ask Professor Ali Munawar that from the question from Mr. Joko. Yeah. Please.
Okay, thank you, Mr. Joko. Well, as said by the rector speech today, he addressed that we are in the process of opening a master's degree program in land reclamations. Yes, in fact, I'm in charge of this plan. I'm I have the chair of the committee for this purpose. Well, it is very important that to open new study programs is to communicate to as much as other parties so that we can get more inputs, what kind of study programs we're gonna develop, what is the content and what kind of needs of the society on reclamation study program. Therefore, today and tomorrow we conduct the international webinar. It's part of how we develop communication with different people with different background to collect all the things that we need to develop our programs. And next month, we are going to conduct a workshop on curriculum of these planned study programs. We're going to invite the different stakeholders from different backgrounds, because as we said in the beginning, that land reclamation, what we talk about related to agriculture, to marginal land, to industrial waste, to mining, and to disaster. So we're going to invite people from different backgrounds so that we can get information and inputs what kind of land reclamation study program we're going to have. It is very important. For that purpose, we're gonna also try to initiate cooperation and collaboration between these different kind of people, like from industry, like from government offices, like from consultant, etc. And we're going to have a cooperation so that our students in our programs can have projects, whatever their interests are. So if their interest is about land degradation because of land reclamation on the mine site, then we can cooperate with mines company to have a final thesis, for example, etc. And also, we're going to have invite speakers, invited speakers from different companies or different offices that are devoted to land reclamation. So that is why it is important to communicate this planned program to different kind of people. And also to conduct the education process, like the need of laboratory, if we have a collaboration with different kind of stakeholders, then we can, share our resource and their resource to for the students. I think that is the plan that we're going to go through, and we plan that next year, inshallah, we're going to open this master's program in land reclamation. Thank you.
Thank you, Professor Ali. I think we still have time, so I will make order from Professor Ali. There is question from Dr. Ernie Johan from Ehime University in Japan. So the question is, you showed a table of heavy metals contents in mine gold, Papua. Yeah, I guess water contamination is also occurred. Do you have data of the heavy metals in water surrounding the mining area? This the question from Dr. Annie Johan. And then for Professor Matswe, there is a question from Dr. Andi from Bapeda Goa in Sulawesi Island, Indonesia. The question is, what is the best chemical composition and structure of clays that required for agriculture activity? Okay, and then for Professor Thomas, there is a question from Miss Rina Kartika from Agriculture Environment Research Institute in Indonesia. The question are how the soil salinity occurred in Australia and how to manage the land recently, and then which part of the land that suffer the degradation here in rangelands or wheat sheep zone or high rainfall land. And there is a question from YouTube. Yeah, that is from Dr. Joko from Universitas Samratulangi, South Sulawesi. Yeah, this area is near Philippines. Yeah, because north part of Indonesia near Philippines. Yeah, I think he is Dr. Joko Purbo, I think, from Department of Soil Science. Yeah, the questions to Professor Azwar Maas. Yeah, decomposition in your term, meaning also degradation that we do not want. So we need to keep compost unaltered. Yeah, it is the question from Dr. Joko. So please, for the first from Professor Ali Munawar, please, time's yours.
Okay, thank you. Ms. Ernie Johan in Ames University in Japan. Well, that's a good question. Yeah, I saw you the seepage from embankment area in which tailings are stabilized over there. So it is possible, very possible, if the seepage is, containing such a high level of heavy metal, then surrounding area, surface water like rivers, they gonna be possibly, highly possible to have elevated heavy metals. Well, right now I don't have data with me, but I can find, and I have friends who work there, and in the future we're gonna work closely with different kind of company, including Freeport. So now, and then unfortunately I've never been in Freeport to see how they look, but we can see and we can find it, informations from Freeport area regarding the environmental degradation from different kind of sources. So we can find it somewhere, and then I'll talk to my friends in there so that I can supply the data. Thank you.
Thank you very much, Professor Ali. And then we invite Professor Matsui. So please, time is yours to answer the question.
So the question was, what is the best clay minerals for agriculture?
Yes.
So,
yes.
The acid resistance is not related to agricultural production.
Okay.
So usually, as you all know, clays with high CC, such as montmorillonite, vermiculite, is a good material for agriculture in the view of cation exchange capacity.
Okay.
Okay.
Okay. Well, thank you very much. Yeah. Very clear answer. Yeah. And then, would you please, Professor Thomas, to answer the question from Ms. Rina, please?
Yes, thank you. Yeah, so the question is about soil salinity in Australia, where it's coming from and how land is managed recently, and which part of the country has most suffered from degradation originating from salinization. The Australian continent is a very, is probably quite special around on the globe, on our Earth. It is, has been hardly impacted by tectonic activities, apart from the eastern coast with subduction of the Pacific plate under the Australian plate, and then the upheaval of mountains, which we know as the Great Dividing Range. And that is a mountain range which very closely along the coast goes from south to north. Everything to the east, everything to the west, to the center of the continent and towards Western Australia, that country has not been reshaped or be impacted by large tectonic activities. Now, a huge part of the center of Australia is built by what is called the Great Artesian Basin. It's a big sedimentary basin to a depth of 3,000 meters. It's about 2,500 to 3,000 kilometers in diameter. And the sedimentation of material in that basin is mainly associated with salts. So the situation which we have is that apart from the very moist zone and or wet zone along the east coast. Wherever we go inland, we have a deficiency of water. In the 1950s and 60s, there has been a program, or maybe even earlier, there's been a program to use water, the groundwater from that Great Artesian Basin for irrigation. So we are, the inland parts, they are dry. We have 300-400 millimeters of annual rain. That is often not enough to have any profound agriculture. And the idea was to use water from that Great Artesian Basin for irrigation purposes. Very quickly, it has been recognized that that water, although there was water, it was too saline and it was actually counterproductive. And that program of exploring all those water resources from the Great Artesian Basin, which are vast, has been stopped for the reason that it only created negative outcomes. And similar, there have been many learnings in other parts where water has been used, which was not really suitable for irrigation purposes or for purposes to prevent salinization of the soil. The question, which parts have suffered most by degradation, that is probably the inland regions, so the rangelands, although they usually, grazing country doesn't require irrigation, but irrigation only happened with the intention to improve productivity and extend the cropping possibilities. I think the salinity problem is well understood in Australia, and government and agricultural interest groups and farmers associations, they have a very good understanding what they can do and what they can't do these days. Thank you.
Thank you very much, Professor Thomas. And now, last but not least, I will invite Professor Azwar Maas to answer the question from Dr. Joko from Department of Social Science, Universitas Unsrat. Please, Professor.
Thank you, Professor Joko. So if we deal with pit soil, the most important is just try to keep the buffering capacity of the pit. Pit can be used for many crops, for example, but don't forget, if we bring input for the crop, the input not only for the crop, but also can be used as nutrient for microbial activity. Let's say the pit pH is very low, even less than 3. If we bring up the pH to 5 by giving, for example, lime, so lime will directly react with peat, liberate soluble peat. That's why don't try to use the peat for optimum yield of the what the crop needs, but try to adopt not so high productivity, but still in having economical value and environmentally safe. And may I also have a comment for the question or comment from Dedi from Sriwijaya. Okay, in Vietnam, they success in even export the rice, because they have one big river that coming from China. They create one way direction of the irrigation. Fresh water always come to the acid sulfate soil. So leaching is most important. In our condition, especially in Kalimantan, we still have two-way direction, irrigation and drainage. And then, let's say 5 kilometers from the main river, the wave, the tidal movement cannot reach out the acidity with area more than 5 kilometers from the canal. So that's why the water quality is still not good. And then now our government tried to have in Kalimantan one-way direction to reduce, let's say, 165,000 development of rice estate in central Kalimantan. We do hope that we may succeed at least double the production with intensity and higher production. Thank you.
Thank you very much. Sorry, my laptop, the battery already down. Okay, ladies and gentlemen, honor speakers, and all attendees, we have completed two circulars of the question and answers, and I think now already 11:25 in West Indonesian time, but in US I think it is midnight. Yeah, midnight time. So thank you very much, especially for the attendees from US. Also Professor Jeff Scotian that also today he attend this webinar. He is the presenters for the tomorrows. Yeah, thank you very much. Yeah, and also I think all presentation and discussions and are very interesting, and I think a very valuable idea and also technology that might be as an alternative solution for land reclamation of the degraded land. Also, this webinar may also as inspiring us to set up and to construct and then open the postgraduate program, especially in land reclamation in our university. And inshallah, the next year we will open the master program. And also, let me remind us that for tomorrow, we still have the second day webinar, and with 3 invited speakers. Yeah, and once again, thank you so much for your attention and then seriousness in participation in these webinars. Let me give appreciation for all presenters, Professor Azwar Maas from Gadjah Mada University, Professor Thomas from Australia, Professor Naoto Matsue from Ehime, Japan, and Professor Ali Munawar from Soil Science Department, Universitas Pembangunan Nasional Veteran Jakarta, as the host of this webinar. And then once again, thank you very much for all. Thank you. Yeah, and see you tomorrow morning from 9 a.m. And for the Western Indonesian time. Bye-bye.
Thank you very much.
Thank you very much. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Warahmatullahi wabarakatuh. Thank you. Thank you. See you next time. Have a nice day. Yeah. Bye.
Thank you, everyone. It was
Thank
very
you,
interesting.
Professor Azwar.
Thank you.
Very interesting.
Bye, Ali.
Thank you, Thomas.